Okay, so you know all the buzz around scaling laws for these large language models. Well, turns out there's a bit of a catch.
Hmm.
They're amazing at predicting how well a model will perform, but only when it's dealing with the same kind of data it was trained on.
Right.
So if you switch up the data set, things get a little fuzzy.
Huh.
But you sent us some research, like this paper, Loss-to-Loss Prediction, Scaling Laws for All Data Sets.
Yes.
That's digging into how these models actually behave across different data sets.
And this is where things start to get really interesting. You see that this research suggests that we might be able to actually predict
Oh, wow.
how a model will do on a brand new data set just by looking at its performance on a previous one. It's like finding this hidden connection between how models learn something that goes beyond the actual content of the data itself.
Okay, so that's a pretty bold claim.
Yeah.
How are they even going about measuring something like that?
Well, they're zeroing in on this concept they call loss-to-loss prediction. And essentially, they found that there's this predictable relationship between the errors or losses a model makes during training on different data sets. And this relationship holds up surprisingly well, even as the model size and the amount of data changed.
So you're saying it's not just random, there's an actual pattern to how these models learn, even across different domains.
Exactly. They put this to the test by analyzing 6 very different data sets, think web text code, academic papers, the whole gamut.
Wow.
And what they discovered was remarkable. The relationship between the losses on these diverse data sets actually followed a consistent mathematical pattern.
Hold on. So you're telling me that a model that's been trained on, let's say, lines of code could somehow tell us how well it would understand a poem?
That's the gist of it. It's like they've stumbled upon a universal language of learning that transcends the specific content of the data.
That is mind-blowing.
To map out these relationships, the researchers used this technique called joining, where they compare models of the same size trained on different data sets, and that's how they were able to see those consistent patterns emerge.
I mean, this all sounds very impressive from a research perspective, but I have to ask, why should we even care? What's the practical use of all this?
Well, consider the sheer amount of resources that go into training these massive language models.
Oh, yeah, it's a ton.
If we could accurately predict how well a model will perform on a new task before we invest all that time and computing power,
Yeah.
it would completely revolutionize how we develop and deploy AI.
So it's like having a shortcut to figure out which models are best suited for certain tasks,
Exactly.
potentially saving tons of time and resources. That's a pretty big deal.
Absolutely. And what's even more fascinating is that this loss-to-loss prediction method actually seems to be more accurate than traditional scaling laws, especially when we have limited data on a new task.
Okay, so we've established that this is some groundbreaking stuff. Now let's get into the nitty-gritty of how they actually measure this loss-to-loss prediction. I'm seeing here that they've broken it down into 3 different types: train to train, train to test, and test to test.
Yeah.
Sounds a bit like a tongue twister, but I'm sure you can break it down for us.
I'll give it a shot, sure. So let's start with train to train. Imagine you're teaching a model to write different genres of fiction. Train to train is kind of like predicting how quickly it'll learn to write sci-fi based on how quickly it picked up fantasy.
Okay, so we're looking at how well it learns on one data set and using that to guess how it'll do on a different one.
Exactly. Now, train to test takes this a step further.
Okay.
It's like saying, okay, we know how fast our model learned to write fantasy. Now, can we predict how well it'll actually score on a test of its sci-fi writing skills?
So instead of just predicting learning speed, now we're talking about actually predicting how well it performs on a whole new task.
You got it. And then we've got test to test, and this is where things get really wild. This is about predicting how a model will perform on one task based on how it did on a totally different task, even if they were trained on different data sets.
Okay, I need a real-world example here. I'm having trouble picturing this.
Sure. Let's say we have one model that's been trained on English and then tested on its ability to write French poetry.
Okay.
And we also have another model that was trained on Spanish and tested on that same French poetry task.
Got it.
Test-to-test prediction would let us take the results from both of these models and use them to predict how well that Spanish-trained model might perform on something completely different, like translating French literature.
Whoa, that is mind-bending.
Yeah.
It suggests there's something really fundamental about how these models learn something that goes beyond the specific tasks or data sets.
It really does. And it opens up a whole new set of questions about the nature of learning and intelligence, both artificial and biological.
Definitely. One of the things that I found most interesting in this research was that they discovered that the optimal size of a language model, the size that gives you the best bang for your buck computationally, seems to stay pretty much the same across different data sets.
Yeah.
That's a pretty significant finding, right?
It is. We tend to assume that bigger models are always better, but this research suggests there might be a point of diminishing returns. Even if you have unlimited data, there's a sweet spot for model size, and it's surprisingly consistent.
So it's not just about throwing more computing power at the problem. It's about finding that optimal balance between size and efficiency. This could have huge implications for how we think about scaling AI in the future.
No doubt. It might mean we need to shift our focus away from simply building bigger models and towards finding more efficient ways to train models of that optimal size. This research gives us new tools to approach that challenge.
For those listening who might be thinking this is all very cool, but how does any of this help us actually build better AI? What are the tangible benefits here?
Well, for one, it could help us make better decisions about which data sets to use for training our models. If we know that performance on one data set reliably predicts performance on another, we can be much more strategic about how we choose our training data.
So instead of just throwing all the data we can at a model, we can actually be more selective and tailor the training process to the specific tasks we wanted to excel at.
Precisely. And remember, transfer learning, that ability of a model to apply knowledge from one area to another, this research sheds light on how that process works and could help us develop models that are even more versatile and adaptable.
Okay, so now I'm curious. Did the researchers come across anything surprising or unexpected in their findings? Anything that kind of challenged their initial assumptions?
Yeah, there was one finding that stood out. It's about the relationship between a model's training loss and its actual performance on downstream tasks. Sometimes, as you might expect, decreasing the training loss actually leads to diminishing returns on those real-world tasks.
That makes sense. You hit a point where just having more general knowledge doesn't necessarily translate into specific skills, but you said there was something unexpected. So what was the surprise?
Well, in some cases, they found the exact opposite.
Really?
Yeah, as the model got better at its initial training task, the returns on the downstream task actually increased. It's like they were unlocking hidden potential within the data.
So it's not just getting better at the first task, it's actually becoming a better learner overall.
That's what it seems like. And this tended to happen when the downstream task was kind of like a hidden gem within the initial training data, something that only larger models could really pick up on. It highlights this really complex interplay between model size data complexity and the specific tasks we're asking them to perform.
It sounds like this research is really pushing us to rethink some of the traditional assumptions we have about how we scale and train AI models.
It is. For a long time, the prevailing wisdom was that bigger is always better. Just keep scaling up the model and the data and you'll get better results. But now it seems like there's a lot more nuance to it. There's an ideal model size. The relationship between training loss and downstream performance isn't always clear-cut, and the choice of training data matters more than we initially thought.
So we're moving away from this one-size-fits-all mentality to AI development and starting to appreciate the more subtle interplay of all these different factors.
Exactly. It's like the difference between mass production and crafting something bespoke.
So instead of trying to build one giant all-purpose AI, maybe the future lies in creating smaller, more specialized models that are optimized for particular tasks or domains. Kind of like building a team of AI experts instead of one AI generalist.
That's one promising direction, and this research gives us a framework for how to do that effectively. By understanding those loss-to-loss relationships between different data sets and tasks, we can actually engineer models that are much more targeted and efficient.
Okay, so we've explored some of the practical benefits of this research, but I'm curious, what do the researchers themselves have to say about the future directions of this work? What are they most excited about exploring next?
They highlighted a few really interesting areas. One thing they're really keen on is using these loss-to-loss relationships to actually guide data selection and filtering. Imagine being able to use these insights to automatically pick the best training data for a specific task.
Oh, wow, that would be amazing. It would take so much of the guesswork out of model development.
Right.
And could lead to even more efficient and effective AI systems.
Exactly. And it could also help us address some of those concerns around bias and fairness in AI.
Right.
If we can develop algorithms that automatically choose training data that's more representative and unbiased, we could take a big step toward building AI systems that are more equitable.
So it's not just about performance, it's about ensuring these systems align with our values as a society.
Absolutely. The researchers are also really interested in developing a more solid theoretical understanding of why these loss-to-loss relationships exist in the first place.
Okay.
They suggest that maybe studying simpler models could help uncover those fundamental principles that govern how these models learn and generalize.
It's like they're searching for a grand unified theory of AI learning.
You could say that, and I think that's one of the most exciting aspects of this research. It's not just about incremental improvements.
Yeah.
It's about potentially revolutionizing how we think about artificial intelligence and its role in the world.
I'm still a bit puzzled by how these models can bridge such vastly different domains, like predicting performance on code based on training on natural language. Do the researchers offer any insights into how this cross-domain magic actually works?
That's a question that's still very much up for debate. They offered a few intriguing hypotheses. One possibility is that all these models, regardless of their training data, are kind of converging on a set of features that share some high-level properties. It's like they're learning this common language of representation, even though the specific vocabulary might be different depending on the domain.
So it's not that they're understanding the content itself, but more like recognizing underlying patterns and structures that are shared across different types of data.
That's one interpretation. Another possibility is that even data sets that seem totally different, like code and natural language, might actually have more in common than we think. Perhaps there are these subtle but significant overlaps in the way these different types of information are structured and presented.
It's like discovering hidden connections between seemingly unrelated fields of knowledge. Who knows what other surprises we might find?
That's the beauty of scientific discovery. We're constantly pushing the boundaries of what we know, challenging our assumptions, and revealing new layers of complexity in the world around us.
Well, this deep dive has definitely given me a lot to ponder. I'm starting to see scaling laws in a whole new light, and I'm excited to see where this research leads us in the coming years.
Me too. It feels like we're just scratching the surface of understanding these incredible learning machines.
This research really opens up so many new questions about how we think about AI, how we design experiments, and even how we define intelligence itself.
It's a real paradigm shift. One of the most thought-provoking questions it raises is whether these loss-to-loss relationships hint at some deeper, more universal principles of learning.
Yeah.
Could it be that the way these artificial neural networks learn has parallels with how our own brains learn?
That's getting into some pretty deep philosophical territory. But I love it.
Yeah.
It makes you wonder if there are fundamental laws of learning that apply across different substrates, whether it's silicon or biological neurons.
Exactly. And if we could crack the code of those fundamental laws, it would have profound implications not only for our understanding of AI, but also for how we understand human intelligence. It could even lead to new insights into how we learn, how we solve problems, and how we adapt to new situations.
This makes me think back to something you mentioned earlier about the importance of context in learning.
Yeah.
It's not just about memorizing facts. It's about understanding how those facts relate to each other, how they fit into a larger framework of knowledge.
Right.
And it seems like these AI models are starting to grasp that concept of contextual understanding.
That's a key point. And it's one of the things that really sets these large language models apart from previous generations of AI. They're not just pattern matching machines. They're developing a more nuanced understanding of the relationships between words, concepts, and ideas.
I'm thinking back to those examples of cross-domain prediction, like using performance on code to predict performance on poetry.
Right.
It suggests that these models are learning to see beyond the surface level of the data and actually extract deeper, more abstract representations of meaning.
That's right. It's almost as if they're developing their own internal models of the world. Models that allow them to connect seemingly disparate pieces of information in meaningful ways.
Okay, so I have to ask, what are your personal thoughts on all of this? Where do you think this research is heading, and what excites you the most in the field of AI right now?
That's a tough one. There's so much happening so quickly. But I'm particularly fascinated by the potential for AI to augment human creativity and problem-solving abilities. I don't think AI will ever replace human intelligence, but I do believe it can become this incredibly powerful tool for amplifying our own cognitive capacities.
So instead of an AI takeover, we're talking about an AI collaboration.
Exactly. I think the most promising future for AI lies in partnerships between humans and machines, where each partner brings their unique strengths to the table.
That's a much more optimistic vision than the dystopian scenarios we often hear about.
And I think it's a more realistic one. AI is a tool. And like any tool, it can be used for good or for bad.
Right.
It's up to us to guide its development in a way that benefits humanity as a whole.
Well, this deep dive has certainly left me feeling hopeful about the future of AI. It's exciting to see researchers pushing the boundaries of what's possible while also being mindful of the ethical implications.
And it's a reminder that we're still in the early stages of this incredible journey of discovery. Who knows what amazing breakthroughs await us in the years to come?
Well, one thing's for sure, we'll be here to cover it. Thanks for joining us on this deep dive into the fascinating world of scaling laws and loss-to-loss prediction. Until next time, keep exploring and keep learning.